demonstration. And one of the most important things to notice in this demonstration is that we very definitely saw evidence of a chemical reaction. We started with two clear colorless solutions. When we got done, we ended up with a cloudy solution. So if we're going to build a story to explain what happened here, we're definitely going to need a balanced chemical equation. So working with your team, take a moment and write a balanced chemical equation for the reaction that can occur between the two components here. And our two components, remember, are barium hydroxide, which was an aqueous solution, and sulfuric acid, which was also an aqueous solution. All right, so predict the products and write and balance the chemical equation, please. So hopefully you identified this as a double replacement reaction where we have barium ions and hydroxide ions and hydrogen ions and sulfate ions. I trade my partners. The barium and the sulfate can get together in a 1-to-1 ratio because barium is +2 and sulfate is -2. The hydrogen and the hydroxide can get together in a 1-to-1 ratio to make HOH, and it takes 2 of those to get it to balance. And then we look at that and go, oh, I kind of recognize that compound. Maybe instead of thinking of this as 2HOH, maybe it's advantageous to think about this instead as being 2H2O. So the things that I made in my beaker were barium sulfate and H2O. I know that the water is a liquid, so it can't possibly be responsible for the white cloudy stuff that I'm seeing, which must mean that the white cloudiness came from the barium sulfate. This must have turned into a solid. Okay, so now we have our chemical reaction. We're going to start the story at the top flap level because the top flap level tells us about our balanced chemical equation. It represents things in the format that we can see them in the balanced chemical equation. It makes very clear the ratios from the chemical equation. So we're going to start at the top flap level and then dive to the bottom flap level once we've got the top flap part figured out. So in the beginning, we had some barium hydroxide in a beaker, and I've chosen to draw 2 particles. And when I put the light in here, the light lit up, and it was very bright. Then I started to add sulfuric acid. We're going to do this one sulfuric acid particle at a time. So I'm going to add one H2SO4. Now that H2SO4, because it's aqueous, also comes with a couple of water molecules along for a ride. So we'll throw those guys in as well. And now we're going to use a little bit of lasso chemistry. Our balanced equation says 1 barium hydroxide reacts with 1 H2SO4. So I'm going to bundle up my 1 H2SO4 with one of my barium hydroxides to create basically one batch of this chemical reaction. So there's one batch of the chemical reaction. According to my equation, this makes a barium sulfate, which is going to be in the solid state, and 2 H2Os. And as I look in my beaker up here, I can see that the white powdery stuff is starting to settle down to the bottom. So I'm going to draw my barium sulfate down on the bottom. So here's a barium sulfate. And we saw that this, for some reason, seems to have formed a solid. Now, you don't need to understand why that formed a solid. We're just going purely on our observations here. We saw it happen. That formed a solid. That's what we're kind of stuck with as our story. In addition to the 1 barium sulfate, one batch of reaction also makes 2 water molecules. And now I'm going to pack this up and say this is one batch of product. And so out of our one batch of reactant, we got this one batch of product. But we also had some leftover stuff. The leftover stuff didn't leave the beaker, so we got to drag the leftover along for the ride. So here's my barium hydroxide that didn't get used up yet, because I didn't have enough sulfuric acid. So that was my leftover one, just brought along for the ride. And then we have a whole bunch of water. We've got 1, 2, 3, 4, 5, 6 that we had to start with. A couple more came along with the sulfuric acid. There we go. 8 water molecules for the purpose of doing the dissolving. Now, one of the things you may have noticed is that some of the water molecules I drew them as H2O, and some of them I just drew them shorthand. Here's the general pattern for what's going to be useful here. Maybe we'll just do it down here. I've chosen to draw some of these as full-on molecules because these were water molecules made by the reaction. I have to be able to see them as hydrogens and oxygens because I have this rule that says whatever I started with, I have to finish with the same atoms. And if I don't draw these new water molecules that got made by the reaction as H2Os where I can actually see the 2 hydrogens and the oxygens, it looks like I'm kind of out of balance on the conservation of mass. These other molecules that I've chosen to shorthand are just water molecules that are doing the dissolving. We're not really counting their individual atoms as part of our conservation of mass. We are counting to make sure that however many we started with, we finished with, and that's why we counted the 4 here and the 2 extras, and we made sure that we put 6 in the next beaker. But we don't actually need to count their individual atoms because they're not part of the chemical reaction. When we arrived at this point in the reaction, with 1 batch done, my light bulb was still on. But the light bulb was getting more dim. Well, if we want to tell the story of what's going on with the light bulbs, that takes a deeper look into what's happening here. And that's where the bottom flaps come in. When our light bulb was nice and bright, it's because the barium hydroxide looked like this. We had 6 free ions. They were ions that had been freed from their partner, and they could move around. The only way ions can conduct electricity is if they're detached from one another, and the positive ion can go one way and the negative ion can go the other way. So here we have 6 ions that are free to move around. Now we're going to generate a bottom flap picture of this situation. Up here we have the barium hydroxide, just like we did here, which must mean that at the bottom flap, this barium hydroxide looks like it does here. So let's put that one into place first. We know exactly what it's supposed to look like. It was the leftover, nothing changed. But then we have the stuff that was made by the chemical reaction. This barium hydroxide down here went with our sulfuric acid to make our first batch of the reaction. So the H2SO4 was actually reacting with those 3 ions right there. And if I peek back at my top flap, I can see what I made. I made 2 water molecules. They're molecular, so I get to move them to the bottom flap just the way they are. Those molecular compounds don't change as you move from the top flap to the bottom flap. And then I made a solid ionic compound. Ionic compounds in their solid state just stay as is, but we can see their ions. So solid ionic compound, there's our barium. Here's our sulfate. And because it was a solid, that's my reminder. Don't pick that one apart. It didn't dissolve for some reason. And then we have to have all the water molecules that we're doing the dissolving. So here's 3, 4, 5, 6, 7, a grand total of 8 of those. And my single batch of reaction is those pieces right there. So my first batch made all of that. In making that, we basically took some of the ions and we captured them so that they can't conduct electricity anymore. We captured 2 hydroxide ions and turned them into water, and we captured a barium ion and stuck it to a sulfate so that it's no longer free to move around. We ended up with only 3 free ions by the time we did this first batch of reactions. And so we went from 6 ions that were capable of conducting electricity to only 3 ions that are capable of conducting electricity. So it stands to reason that we would have gone from a light that was bright to a light that was substantially more dim because we don't have as many ions available to conduct the electricity. So while the barium hydroxide is a great conductor of electricity and the sulfuric acid is a great conductor of electricity, mixing them together actually causes a chemical reaction and gets us entirely different things. And that's how it is that we can mix two things together that both conduct but have the light bulb get dimmer as time goes on. So you and your team are going to take this forward from here. The next picture is going to involve adding one more H2SO4, which is aqueous, so we'll bring a couple water molecules along for the ride, and getting yourself to the point that the light bulb is turned off. And then adding another H2SO4. And because it's aqueous, a couple water molecules that go with it. And getting yourself to the point that the light bulb is starting to turn back on again. Okay, so the first thing you and your team are going to do is you're going to finish the story in pictures. Once you're done with that, you're going to proceed to part 1 of your practice test. Step 1 is done. You watched the demonstration. You watched me get the picture started. You will have drawn the remaining pictures and added the top flaps and associated drawings to your story. And then you're going to do a little bit of graphing work. With this demonstration, we could have used a conductivity tester instead of the light bulb to get some numbers. And if we had done that, these are some graphs that could have been generated. So you're going to finish up part 1 of your practice test based upon the demonstration and the top and bottom flap pictures.